Hey Opties! Today we're talking about rigid transformations. You may have heard of this in geometry. When we talk about this in geometry, we're talking about reflections, translations, and rotations. But when we talk about this with functions, we don't have rotations, but we do have translations and reflections. So there are certain things that happen in our equations and our graphs that tell us what sort of transformations are happening. When it's a rigid transformation, it preserves the size and the shape of our function. It doesn't distort its size or its relationship between its x and y's. It will just be a different movement on your graph or a different orientation. Movement going with translations, and orientation, if it's like setting upright or setting flipped this way or upside down, that would be change in orientation, which would occur from a reflection. So let's take a look at what happens if we have an x-axis reflection. So we see if we have f of x, that is a negative out front of f of x. So it's a negative f of x. That's what happens in an x-axis reflection with our equation. And we'll see that in specifics in a moment for specific function families. What happens with our x's is they stay the same. Your x's do not change. If you're reflecting over the x-axis, remember that's that horizontal axis, your x's, well, they're gonna stay the same. What happens with your y's is they change sign, okay? So reflecting over the x-axis changes your y's. So it's kind of like the two different letters, right? X-axis, you're reflecting like this because your x-axis is a horizontal line. So your y's are what are changing. You're changing your orientation about vertically, right? So you're affecting your y's. So let's look at what happens for a parabola. Let's say you just have the parent function f of x is equal to x squared. If you want to do an x-axis reflection, it will look like this. This darker green would be that negative f of x. So what I've done is I put a negative on both sides of the equation, okay? So it's almost like we're just manipulating that equation. So there's a negative on the outside of f of x. So there's the negative on the outside of everything on our function. So negative x squared. Similarly, we have negative the square root of x. And that has been a reflection over the x-axis, okay? And again, similarly, we have negative x cubed. So I think the x cubed looks really cool when it's a x-axis reflection because it's real pretty and symmetrical, which these are, of course, because if you're reflecting about a line, you're still gonna be symmetrical regardless. But it looks kind of pretty because this down piece on the left part of your function for the regular x cubed now becomes an up piece. And the up piece on your right of the original x cubed now becomes down and right. So you can see that it reflects over that x-axis and it looks interesting. Let's take a look at y-axis reflections. So notice we don't have a negative on the outside of our f of x, we have a negative on the inside. So it's on the x itself and it's inside the parentheses. Now your x's change sign, but your y's remain the same. Okay, so this is like flipping this way. Reflecting about that y-axis is gonna change your x values, more like this honestly, unless you're just kind of straddling that y-axis, okay? So let's take a look at our parabola. Now this looks interesting. You don't see any light green, which is supposed to be your parent function, because your parabola of just a regular x squared already straddles the y-axis. When I mean straddle, it's like equally on both sides, right? If you're riding a horse, you're straddling the horse, right? Both legs equally on the horse. So you're straddling that y-axis. If you flip it, it stays exactly the same. So what we know here is that an x squared, just a parent function of a parabola, of a quadratic function, it's symmetrical about the y-axis. And we can tell that algebraically too. Let's say we put a negative in front of our x value. Let's say we put a negative on our x inside the parentheses. So we see that the quantity of negative x squared, that's what happens when we put a negative on our x inside the parentheses. But that just means negative x times negative x. And what is that? That's just a positive x squared. It's the same thing, because a negative times a negative is a positive, just like a positive times a positive is a positive. So it doesn't change. So that's another way to tell that it has some y-axis symmetry. Here's another little tidbit. If you have y-axis symmetry, you are called an even function. So that's a little extra thing for you. You're welcome. Now let's look at our square root function. So f of x is equal to the square root of x now becomes f of negative x equals the square root of negative x. So we've put a negative inside of our parentheses, but our square root is like a grouping symbol. We don't technically have our parentheses here. We could write parentheses, it would be okay, but we don't need them. So we could write that if we wanted to. Now here's something I find interesting. If you think about how we talked about in our domain and range video, we had domain danger zones. One of those was having a negative underneath our square root. So at first glance, you might think, what in the world? We've got a negative x. Isn't everything going to be negative? Well, if you substitute a negative number in for your x, you'll have a negative, negative, and that'll become a positive, right? It's a negative times a negative is positive. So the danger zones for square root of negative x would actually be positive x values. And you can tell that in our graph. Let's take a look. There is no dark green curve on the positive x side. So not in the first quadrant or the fourth quadrant. That would be all of our positive x's, right? Because if you do have a positive x, let's say you substitute positive 3. The square root of negative, and then you substitute the positive 3 for x, that is going to remain a negative underneath your radical, which is a domain danger zone. So that's something interesting to consider. Even though our function has a negative x on the inside, it's not a domain danger zone for everything. For it would just be for whenever whatever x is makes it be negative underneath the radical, which would be positive values. On the flip side, if you substitute a negative x value into our parent function, then it would be a domain danger zone. Notice there's no light green on the negative x side, okay? So that's how our domain danger zone plays out there. Let's take a look at our parent function of our cubic and see what happens there. Take a look at this graph and this graph. Isn't that strange? Don't they look exactly the same? Well, let's look at our equation here. F of negative x equals negative x cubed, the quantity of negative x cubed, so all of it, right? Well, that's negative x times negative x times negative x. Well, a negative times a negative is a positive, so that'd be positive x squared times another negative x is still going to end up to be negative x cubed. So algebraically, they end up the same, whether you put a negative on the outside of your f of x or on the inside on your x. So the graphs and the transformation of these are the same. Really cool. Let's take a look at translations. You know, on that, what's that song called when they're like, slide to the left, slide to the right. I guess in your view, it'd be slide to the left, slide to the right. That's like a translation. You're just sliding around. A translation is a slide. That helps you remember. A reflection is a flip. That helps you remember. So let's take a look. We can either slide to the left and the right, or we could, what's they call it? They're like hop or jump. I know they say that in the song too. Jump. I don't know how they say it. I forget. But you know, if you jump, you're going up and down. That would be a vertical translation. So let's take a look. F of x goes to f plus or minus c. So you're adding or subtracting inside your parentheses for a horizontal translation. That's going to be left and right. So we'll discuss in a moment which one's left and which one's right for your add or subtract. So what happens is your x, since you're doing horizontal, that's going to be left and right. Your x-axis is horizontal axis, so it's only affecting your x values. Your y values just stay the same. So let's take a look at our parent function of quadratic. If you subtract c, that's going to go right c units. So wouldn't you think subtract would go left? Actually the other way around. So the horizontal, it actually goes opposite of what you would think it would be. Look at here for our square root of x. If you do plus c on the inside of your parentheses or your grouping symbol, such as a square root, you're actually going to go left c units. Notice we have our c here. That tells us we've gone right c. And that's a negative c. We've gone c to the left. Let's look at our point to ponder, which discusses this. Notice minus c yields a right shift and plus c yields a left shift. The sign of c and the direction being opposites always occurs in horizontal translations. So remember, for horizontal translations, if it's plus, it's actually to the left. If it's minus, it's actually to the right. So it's the opposite direction that you would think. Let's look at our final rigid transformation, which is vertical translations, which would be up or down. What you're going to do here is you're going to add or subtract on the outside of your function. If you're writing it kind of the way most functions are written, it's going to be really at the end. It doesn't have to be, as long as it's outside of your grouping symbol. But typically it's at the end. Your x's stay the same because it's vertical. You're not affecting your horizontal axis. You are doing plus or minus on your y, which is what we see here. Y goes to y plus or minus c. Depends on whatever you're doing. So let's take a look for our quadratic. If we subtract c on the outside, then we go down c units. We can see that it's from the light green to the dark green. We've gone down c. If we add c on the outside for our square root or for any function, we're going to go up c. Now let's look at our cubic. We have subtracted c on the outside and we've gone down c. So for vertical, it's a little less confusing than our horizontal. If you're adding, you're going up, just like you'd think. And if you're subtracting, you're going down, just like it makes sense, right? Because you're going towards the positive y's and you're going towards the negative y's. I want to show you one example for our horizontal shift, so it makes a little bit more sense with an actual example of why it changes. So let's say we have f of x equals the quantity of x plus 1 squared. So let's say we just want to see the difference between a regular f of x equals x squared and f of x equals x plus 1 quantity squared. So let's say we have g of x is x squared. So let's just substitute, say 2. It's kind of an easy number to deal with typically. So g of 2 is 2 squared, which is 4. So if we're testing the theory that a plus 1 on the inside would actually take us left 1, which would subtract 1 from our x values, because we're going left, right? We're going to have to substitute a 1 for f of x, and we should get 4, okay? So let's do that. F of 1 equals 1 plus 1 squared, which is 2 squared, which is again 4. So it's taken our x value, and we still get the same y value from taking our x value one place to the left. So you see, even though it's a plus 1, we've gone left 1. All right, Opties, that's it for rigid transformations of functions, including reflections, x-axis and y-axis, and translations, which would be vertical and horizontal. See y'all next time.